Hello everybody and welcome back to a mathematical rhapsody. In this video we will be talking about, as I said in the last class, intermolecular and intramolecular forces, right? So this is a very important concept and with this things become suddenly interesting, right? So let's start. In the last class we discussed about electronegativity, right? And we discussed about how a bond can be ionic or let's say polar covalent or non-polar covalent. Let me give you a quick example of another let's say ionic bond. Let's consider NaCl. We know it's the most common one that you can see. You all might know that it's an ionic. It contains an ionic bond, right? So let's consider this to be a covalent bond. Let's draw a bond like this. This is Cl. What happens is chlorine, which has an electronegativity of 3, this has an electronegativity of 0.9 rounded off, with the difference is greater than 1.7, 2.1, right? So it completely grabs the electron from sodium. So this has a complete positive charge while this has a complete negative charge. Right. Now let's discuss about intermolecular and intramolecular forces. We are going to discuss about dipole-dipole interactions. Then you have hydrogen bonding. Then you have London dispersion forces. So let's start. Let me take. Okay. Now let's take a quick example of dipole interactions. It is between two poles, as you can guess. Okay. Let's take acetone. This acetone has a formula of C3H6O. Let me just draw that. O is double bonded to carbon, which is again bonded to CH3, say, and you have CH3. Right. So let's draw another acetone. This is what? This is acetone. Let me draw another acetone with the blue. Okay. This will be H3C, CH3. Okay. Now look here. What happens, as we discussed, carbon has an electronegativity of 2.5, and this guy here has 3.4, oxygen at 2.5. So as we saw, the electrons are most probably found around oxygen than around carbon, right? So let's see what happens in between these two molecules, right? And I almost forgot to tell you, intermolecular forces are those which take place between molecules, and intramolecular forces are those which you can see in molecules, within molecules, right? Between carbon and oxygen, between this carbon and this carbon, this carbon and this hydrogen, this carbon and this hydrogen, and so on. But intermolecular forces are what we're going to discuss now. Okay. We know that carbon has a partial positive charge while oxygen has a partial negative charge. Same here, partial positive. This is a partial negative. Oh, I'm sorry, I didn't see that. Right. Small one. This is a partial negative charge. And now, as you can see here, this is partial positive and this is partial negative. As we know, opposite charges attract. But this is a very weak force of attraction since it's only partial, right? So this is exactly what is called a dipole-dipole interaction, right? Since it's very weak, the boiling point is less compared to others. Boiling point is less, about 56 degrees Celsius. Okay, now let's talk about hydrogen bonding. Okay, hydrogen bonding. Hydrogen bonding. Okay, hope the time doesn't run out before we complete this. That would be really, really sad. Okay, so as you can guess from its name, hydrogen bonding is the force of attraction that you can see when a compound contains hydrogen, right? Two molecules of that compound attract each other due to hydrogen, right? Let's take an example, the most common example, water. You know the structure of water. It goes something like this is hydrogen, this is hydrogen. As you can guess, this has a partial positive charge, the partial negative charge, and this too has a partial positive charge. Okay, now let's draw another hydrogen. Let's see, water atom, water molecule. I'm sorry. Let's start with blue. This is another water molecule. This is partial positive, this is partial negative, this is partial positive, right? As you can guess, as we discussed, this hydrogen right here, this hydrogen will be attracted towards this atom, this atom of oxygen, since hydrogen is partially positive and oxygen is partially negative, right? This is exactly what keeps molecules together. This is not if you check in a gas, let's say nitrogen for instance, any gas, they just move around because they don't have that much of attraction as this, right? Let me just tell you one thing. Individual hydrogen bonds, this is a hydrogen bond are weak, but when you look at the whole, they are really strong. They keep millions of molecules together. Let me just draw another molecule here. This no, not this color. No. Okay, let's see. Let's start. Okay, this is a partial negative charge. This has hydrogen partial positive. This is hydrogen partial positive. Right. So this hydrogen bond is very important. Since it's strong, it keeps these molecules together, and for them to vaporize, for water to vaporize, we need a much higher boiling point than acetone. It has a boiling point, as you all know, of 100 degrees Celsius. Okay, so this hydrogen bond is exactly what causes cohesion and adhesion, which we will be studying about after we complete London dispersion forces, right? Okay, so let's talk about London dispersion forces. Let me go here. So hope you understood. It can happen in many atoms such as CH4, but here it is almost neutral, so we won't be talking about that. But this is one of the main examples that you have to keep in mind if you ever want to clarify your doubts about hydrogen bonding. Okay, let's move to London dispersion forces. London dispersion forces. Right. Let's see. Now these are very, very weak forces, right? These let's say they are only temporary, if you can call it that. You know that electrons keep moving around you know that electrons are in continuous motion. So let's take an atom for example. Let's say this is an atom. This is the positive charged body inside. But anyway, let's complete this London dispersion forces, and then we'll stop with our session today. Okay, this is an atom. Now, since the electrons are in random motion, in let's say that more electrons at one point of time were found here. These are electrons. These are electrons. Okay, and at the same time, since you know that let's say at the same time another atom the same kind has electrons. Sorry, let me just draw that there. Okay, this is the positive charge. Only a less amount of electrons are on this side, and more amount of electrons of this atom or molecule are there in this side, right? So since you know this creates a partial negative charge and this creates a partial positive. The electrons are there, but the positive charge over here dominates these electrons. So that is why there is a partial positive charge there. This will contain partial positive, partial negative. Now, since they are partially positive and partial negative, these ends will attract. These ends will attract. Now, this is what is called a London dispersion force. Now, this is very, very weak. Okay, now let's see, for example, as I told you, CH4, right? It doesn't have a hydrogen bond, but in fact has London dispersion forces. C, okay, and you have hydrogen, and you have hydrogen, and you have hydrogen. Now, some of the atoms, some of the electrons, more amount of electrons have come here, so this creates a partial negative charge. And let's take another molecule. Less amount of electrons are present here at one time, so there will be an attraction here. Okay, so these are called London dispersion forces, right? But these are very important in non-polar covalent molecules. Thank you.